So I guess we could start off with some of the more foundational concepts of this course, backed by some formulas that should be very beneficial to know while doing your interview, and ultimately ending it off with a couple of questions that stitch everything together.
Sounds good.
The force equation, or Newton's second law, F equals ma, where F equals force, m equals mass, a equals acceleration. What this means is if a force is applied to an object with mass m, it accelerates in the direction of the force. Force is directly proportional to acceleration since mass is constant. Torque is force but rotational. This is how F equals to ma was linear force. Torque is rotational force. It is the amount of force required to make an object rotate around its own axis. It's generally given by the formula torque equals to F into L, where F is your force, L is your distance to your pivot point. You also have another formula, torque equals to I into alpha, where I is your moment of inertia, alpha is your angular acceleration. Now, this equation is also analogous to F equals to ma. It's just that F equals to ma is linear force, and torque is your angular force. Now, you might be wondering, moment of inertia, I've heard of that term, but what does it mean again? Well, moment of inertia is a measure of an object's resistance to change along a rotational axis. For example, let's say there was an object rotating along its own axis, and I came in and tried to pull it the other way. If there was a difficult endeavor for me, it would mean that the object itself had a high moment of inertia. But if it was easy for me trying to make it go the other way around, it would mean that the object had a low moment of inertia. Well, you can quantify the value of moment of inertia based on the mass distributed along its axis. A real-life example would be a figure skater. They would rotate a lot faster if their arms were put together than if they spread their arms outwards, like this.
Close to my body, and I spin around very rapidly. As soon as I move them out, I slow down again. And I can repeat this as many times as I want until the friction of the turntable stops me.
Oh, and by the way, here are some formulas for the moment of inertia for various cross-sections. For a rectangle, I equals 1 over 12 into b into h cubed, where b is your breadth, h is height. For a hoop, it's mass into radius squared, m into r squared. And if it's an irregular-looking object, the total moment of inertia equals the center inertia plus mass into height squared. The energy equations, we've done this in high school, so it's not too bad. Let's start off with kinetic energy. It's the energy possessed by an object due to its motion, which equals to half into m into v squared, where m is mass, v is velocity. Rotational energy, that's half into I into omega squared, where I is moment of inertia, omega equals to angular velocity. Gravitational potential energy is the energy possessed by an object due to its height, m into g into h, which is mass, gravity, and height. And finally, spring energy, which equals to half into k into x squared, where k is spring constant, and x is displacement. The stress equation, stress equals to force over area. It's also interesting to note that pressure also equals to force over area. So what is the difference between pressure and stress? Well, the idea is pretty simple. Pressure equals to the force applied perpendicularly to a surface, while stress is the resistance of the material itself to avoid deformation over that certain area when a force is applied to it. If you apply pressure to a surface, stress is the capability of the atoms inside the material to avoid that force from destroying or deflecting or deforming a specific object. That's the difference. The formula is the same, but the application and use of both these terms are different. There are also two types of stresses found along a cylindrical object, for example, a soda can. You have your axial stress, which is found along the horizontal axis of your soda can, and you also have a hoop stress, which is found along the circumference of your cylindrical soda can. The formula for axial stress is given by the formula P into R divided by 2T, where P is your internal pressure, R is your radius, and T is your thickness, or wall thickness. And you also have a hoop stress, which is the same formula, but without the 2 in the denominator. P into R divided by T, where P is your internal pressure, R is your radius, and T is your thickness of wall. If you look at the relationship between both the stresses, the hoop stress equals to 2 times the axial stress. Something to keep in mind. Natural frequency is the frequency at which a system currently at equilibrium position or a standstill position starts to oscillate or vibrate when an external disturbance is applied to it. For example, buildings tend to have a pretty high natural frequency to avoid it from vibrating or oscillating when a sandstorm hits it or like a wind gushes at it. So yeah, that's the application use of natural frequency. Well, the formula for natural frequency equals to 1 over 2 pi into the square root of k over m, k being the stiffness, m being the mass. This is the maximum deflection that the beam will experience when a force is applied to it. The formula for maximum deflection is given as such. Maximum deflection equals to FL cubed divided by 3e into I, where F is the force, L is the length of the beam, E is the Young's modulus, and I is the moment of inertia. The first question I'm going to talk to you about was a question that I was asked 3 times over 3 separate interviews, 2 technical rounds and 1 HR, and this was, I think, between 2 different companies. So I think this is a pretty essential question to understand, so why not start with this one, right? What we have here is a cantilever beam that is stuck on one side to a wall and has a flag that's mounted on it on the other side of the wall, which means that there's a flag, there's some sort of mass pulling on it, that's why there's some force pulling on it, gravitational force. So that's what's happening here. And since there's some sort of force being pulled on it from this side, the beam is going to deflect at some point, right? It's going to point downward at some point. So our job is to figure out how we could reduce the beam's deflection. How do we stop that completely? How do we keep it from deflecting and keep it straight, basically? How do we do that? So yes, the formula is comparatively simple. All we got to do is understand what this formula is and then explain that to the interviewer. So this is what it is. So the formula of deflection maximum for a cantilever beam equals to F L cubed divided by 3 into E into I. Now F is your force, that's this thing right here. L is the length of your beam, that's this whole thing right here. Now E is your Young's modulus, that's dependent on your material. That is this thing, that is modulus. And finally your I, which is your moment of inertia, that's dependent on the cross-sectional area of your beam. So in this case, I'm assuming your cross-sectional area is a rectangle. As it says in the question, it is a rectangular cross-section, just read it. So we use this information to solve for your deflection. So how do we reduce the deflection of this beam? First things first, we know that deflection is directly proportional to force, right? So if you increase the amount of force pulling on this side, the deflection is going to increase, therefore pulling it downward. Therefore, if you reduce the deflection, if you reduce your force, your deflection decreases too. Second thing is your deflection is again inversely proportional to your length. If you decrease your length, your deflection once again decreases too. If you reduce the length of here, so this is making it shorter, would really help in this case. And now for the bottom, we know that deflection is inversely proportional to your Young's modulus. So if you increase your Young's modulus, your deflection would decrease, which makes sense too, right? Because the higher your Young's modulus, the stiffer the material becomes. If you remember the stress strain curve of any material, the stiffer the material is, the more steeper your Young's modulus line is in your stress strain curve, right? So this curve is a lot steeper than this curve, and both of them are your Young's modulus. I think if you look at the slope. Therefore, yeah, the higher your Young's modulus, the lower your deflection. And finally, your moment of inertia. The formula for moment of inertia in this case for a cantilever beam that's rectangular is I equal to B into H cubed divided by 12, where B is your breadth and H is your height. Therefore, if you increase either one of these 2 points, if you increase your breadth or your height, that would in turn increase your moment of inertia, therefore decreasing your deflections. If you increase your moment of inertia, that would decrease your deflection. If you increase your breadth or your height of your beam, that would also decrease your deflection. So that is how you would answer this question. So here is question number 2. You have beam A and beam B. Both of them are of the same cross-section area and made up of the same material. Interesting. One of them, beam A, is 5 meters long, while beam B is 10 meters long. So beam B is 2 times as long as beam A. Question is, which one is stiffer? Okay, that's not too bad. In order to solve this question, we again use a simple formula and let's plug it in and solve it. The formula for this is K, which is your stiffness, equals to E, and to A divided by length. That's all you need. So we know that K is your stiffness equals to your Young's modulus, which is dependent on the material. A is your cross-sectional area, the area perpendicular to the force that's applied on it, and your length, the length as in this length here. So we can use this formula and solve for which beam would be stiffer than which one and by how much too. Let's look at beam A stiffness. So AA, for example, equals to some Young's modulus into the cross-section area, which we don't know, divided by 5. And beam B, which is AB, for example, equals to E into A divided by 10. Now, I know that both of them have the same Young's modulus because they have the same material, and they also have the same cross-section area as said in the question. Therefore, all you need to do is equate both of them in terms of what is common. So I know that this EA thing is common in both these equations, and all I need to do is plug and chug, right? So EA in this case equals to 5 Ka, and then EA in this case equals to 10 kb, sorry. And therefore, 5 Ka equals to 10 kb, and therefore, Ka is 2 times kb. And what this means is the stiffness of A, right? The stiffness of A is 2 times what the stiffness of B is. Therefore, the beam A is stiffer than beam B, and by 2 times. That's how you answer this question. I was asked this question during a panel interview, so I think this might be a pretty good question to talk about. Now, this question revolves around the idea of buckling and buckling loads. So fancy, right? So it's pretty simple. It's not too bad. The idea is such that you have 2 columns. Both of them are standard columns, standard objects. They're made of the same material, have the same cross-sectional area, and you have a uniform load on top. The only difference between both these columns are the endpoints. This is a fixed column, and this is a pin column. Our job is to figure out which out of these 2 beams has the highest buckling load, or critical buckling load. What that means is if I put a force on both these columns, which column is most capable of withstanding a buckling force that kind of bends it out of shape? So we want the beams to stop doing this, like buckle in a sense, right? Kind of bend inwards, like crack and all that. Which one out of these 2 beams is most capable of withstanding that kind of damage? Is it beam 1 or beam 2? We don't know. Let's find out, right? So how do we approach this? Again, the formula is very simple. We just need to look at a formula, understand what values you're playing with, and that's it. The formula is this. The critical buckling load equals to pi squared E, Young's modulus, into I, moment of inertia, divided by LE squared. Now, what the hell's going on here? We know this is pi, which is a constant, and this is squared. When E is our Young's modulus, that's dependent on the material we use. Since both of them are made of the same material, that's going to be the same again. Moment of inertia, pi, again, dependent on the cross-sectional area of the beam. Now, that is also the same in beam 1 and beam 2, so that's also common. So what do we have going on here? The only thing that's different would be our LE value. So if you look at this, it's technically just PCR that's inversely proportional to our effective length. That's it. So the higher the effective length, the lower our PCR value would be. You've got to figure out what our LE value is for length 1 and length 2, and accordingly we make our judgment. So how do we solve for this? Now, for every beam that has a different endpoint, their fixed point and end pin and whatnot, there is a different value for your LE. So in the case of beam 1, our LE value is basically 0.5 L, and beam 2, our LE value is simply L. That's basically how it is, right? So now, if you look at this, all we got to do is take these values and plug it into our formula and then make a decision. So let's say beam 1's case, PCR is proportional to 1 over 0.5 L squared, which ultimately gives us 4 times L squared. And in the case of beam 2, we have PCR equals to is proportional to 1 over L squared, which ultimately makes this formula, right? So if you look at this, if you compare both PCR values, you know that PCR, or the critical buckling load in case of beam 1, is 4 times as competent, or 4 times as resistive to the buckling load as number 2 is. Therefore, number 1 is stronger or has a higher buckling load than number 2 does. So your answer will be number 1, and that's how you answer this question. We started off with a couple of force equations, torque, moment of inertia, energy equations, stress, natural frequency, beam deflection, and concluded with a couple of engineering interview questions.